Hello, welcome everybody. My name is Abu Naser Masud. I am from the Malardalen University in Sweden. Today I am going to present a method to compute minimal weak control closure. The method is simple to implement and it is both theoretically and practically efficient. Weak control closure is the closure of certain kinds of control dependency relation. So let's start with the definition of control dependency. Control dependency relation expresses that one program instruction controls the execution of another instruction. The formal definition is provided over the control flow graph representation of programs. A control flow graph node M is control dependent on another control flow graph node N if there exists a path from N to M and all the nodes in this path except N pass through M to reach the exit node. Then we say that M post dominates N. And finally, N can reach the exit node without going through M. If all these criteria are met, then we say that M is control dependent on N. This definition is based on the post-dominator relation, which only works if the control flow graph has a unique exit node. Control dependency relation is an important concept in many subfields of program analysis, such as program optimization, program slicing, and software testing. In this work, we focus on the weak control closure relation that captures non-termination insensitive control dependencies. To define weak control closure, we need the concept of V-paths. Suppose N is the set of control flow graph nodes and V is any subset of N. A V-path is any control flow graph path that ends at a node in V, and no node in this path except the start and the end node is from V. However, the start vertex may or may not be from V. Suppose V includes the control flow graph nodes N5 and N8 in this control flow graph. Then N2 to N5 and N2 to N8 are V paths because no node in these paths except the N nodes are in V. N5 to N8 is also a V path because N8 is in V, the intermediate node N7 is not in V, and it does not matter if N5 is in V or not. N2 to N9 is not a V path because this path includes a node N8 which is from V. We can now define the weak control closure. A set B is weakly control closed if all V paths from any node N not in V meet at the same N node when N is reachable from V. For example, if V includes N5 and N8, then it is not weakly control closed because there exists a node N3 and N3 has two disjoint V paths N3 to N5 and N3 to N8 that does not meet at a common node. However, if V includes N3, N5 and N8, then it is a weakly control closed. If V is weakly control closed, then the weak control closure of V is equivalent to V. Weak control closure of V is a transitive closure relation. That means if there exist control dependencies N1 to N2 and N2 to N3, and if N3 is in V, then N1, N2 and N3 are in the weak control closure of V, provided that N1 is reachable from V. The theoretical complexity of computing WCC by existing methods is very expensive. For example, the worst case complexity of WCC computation by Danishik and others is cubic with respect to the size of the control flow graph. The method of Raghunath and others is even more expensive. It is more than quartic. This is not good for the application of control dependency. The theoretical complexity of our method is quadratic in terms of the size of the control flow graph. Thus, we improve the complexity of WCC computation by an order of magnitude. Later, we will see that our method is also practically very efficient. In this work, we consider intra-procedural deterministic programs. We consider control flow graphs which may not have any exit point. That means the program is non-terminating. Or we allow control flow graphs which have at most one exit point. Programs having multiple exit point is not a problem because then we can create a super exit node and all other exit nodes are connected to the super exit node. We also allow control flow graphs which have a non-terminating exit point like this. So if an execution that reaches here cannot proceed any further, that means the program gets stuck here. So we are considering a wide variety of intraprocedural control flow graphs. Now Let us see how we can compute minimal weak control closure efficiently. As we have seen before, a set V is weakly control closed if all V paths from any node n which is not in V meet at the same end node when n is reachable from V. If this condition is violated, then V is not weakly control closed. That means then there exists a node n which is not in V and n has two disjoint V paths ending at distinct nodes. Such nodes are called weakly residing vertices. This is the key concept of computing weak control closure. For example, if V contains the node n5 and n8, then n3 is a weakly residing vertex because there exist two V paths n3 to n5 and n3 to n8 that does not meet at a common node. We can compute WCC in three steps. First, we compute W, which is an over approximation of the set of weakly residing vertices. In the second step, we verify that all the nodes in W are weakly residing and remove all spurious nodes from W that are not weakly residing. At the final step, we discard all nodes from W that are not reachable from V. So finally, the union of W and V is the weak control closure of V. In order to compute an over approximation of all weakly residing vertices, we traverse all V prime paths in the control flow graph from the nodes in V backward, where V prime is the union of V and W is initially empty. If there exists a V prime path, then it is either a V path, since the end element can be from V, or there is a V path going through a node in W. So a V prime path always ensures that there exists a V path. While visiting a node n during this traversal, we consider n as the starting vertex of V prime paths and record the n node of the visited V prime paths in a function a of n. If any node n witnesses more than one n vertex of visited V prime paths, then it is a potential weakly residing vertex and we include n in W. Let us illustrate this process with an example. Suppose V includes n5 and n8. Then n5 and n8 are trivial V prime paths and we include n5 in A of n5 and include n8 in A of n8. We can traverse the V prime paths in any order. While visiting the node n4 from n5, we have witnessed the V prime paths n4 to n5 and record n5, the end element of this path, into A of n4. We continue traversing the V prime paths and record the end node of V prime paths. Thus, n5 is included in A of n3 and A of n2. At some point, we visit n7 from n8 and n7 to n8 is a V prime path and record n8 in A of n7. However, we will not record n8 in A of n5 because n5 itself is a trivial V path. So A of n5 should be n5. After a while, the algorithm witnesses two V prime paths from n3, one from n3 to n5, another one from n3 to n8. So n3 is a potential weakly residing vertex and it is included in W. Then n3 is a trivial V prime path and we replace the previous record of n5 in A of n3 by n3. We continue traversing the V prime paths and recording the n nodes of V prime paths until a fixed point is reached. Finally, we obtain the set W, which is an over approximation of the set of weakly residing vertices. The process that we have illustrated by an example is provided as algorithm 2 in the paper. Then we have proved theorem 1 stating that W is an over approximation of weakly residing vertices. Theorem 2 states that this process eventually terminates, and lemma 2 states that the worst case complexity of this process is quadratic in terms of the size of the control flow graph. The proof of these theorems and lemma are provided in the paper. Now, let us see why the previous fixed point computation gives us an over approximation of weakly deciding vertices. Consider this control flow graph and assume that N6 and N7 are in V. Suppose we have traversed some V prime paths that end at N7 and record N7 into the A function of all the visited nodes. While visiting the V prime paths that end at N6, we identify node N5 as the potential weakly deciding vertex because there exist two V prime paths N5 to N7 and N5 to N6. N5 is then included into W and A of N5 is updated to N5. Since B prime paths can be traversed in any order, N3 and N1 can be traversed before N4, and thus A of N4 is not updated due to the update of A of N5, and eventually N1 will imprecisely witness two V prime paths, one going to N7 and another one going to N5. Thus, N1 will be identified as a potential weakly deciding vertex. However, N1 to N7 is not a V prime path since this path includes the node N5, which is not the start vertex but it is from V prime. This imprecision is obtained due to visiting N3 and N1 before N4. Similarly, N0 witnesses two V prime paths, N0 to N1 and N0 to N7, and N1 is included into W imprecisely since N0 to N7 is not a V prime path. Note that different orders of visiting control flow graph nodes will only give us imprecision, but it will not sacrifice soundness. So at the end, we will obtain W that includes N0, N1, and N5, even though the only weakly deciding vertex in this graph is N5. In the second step, we verify whether each vertex in W is weakly deciding or not. To perform the verification, we generate a directed graph from this control flow graph, the W and V sets and the results recorded in the A function. The set of nodes in this graph is V prime, which is the union of V and W. So we can obtain the successors of a node in this graph by looking into the A value of its successor nodes in the control flow graph. For example, the A value of N5's successors are N6 and N7, and thus these nodes are the successors of N5 in this directed graph. Similarly, the A value of N1's successor in the control flow graph is N5, and thus N5 is the successor of N1 in this directed graph. In the same way, we obtain N1 and N0 as the successor of N0 here. One interesting feature of this graph is that if there exists an edge N to M in this graph, in this directed graph, then N to M is a V prime path in the control flow graph. For example, N0 to N1 or N1 to N5 are V prime paths. N0 to N1 or N1 to N5, they are V prime paths in this control flow graph. The nodes in this graph includes all control flow graph nodes that represent conditions in the program code and the nodes in V. The generated graph is usually much smaller and less complicated than the control flow graph. The verification is performed on this generated graph. The idea of the verification process is simple. First, we set V prime equal to V. We start traversing the V prime paths backward from the nodes in V. When we reach a node in W through one branch, then we ensure the existence of a V prime path in that branch. We also know the end node of this V prime path. Then we look into the successors of other branch and see if we can reach a node in V prime which is different than the end node of the visited V prime paths in the first branch. If we can reach a distinct node in V prime, then we ensure that the visited node N5 in W is surely a weakly deciding vertex and include it in V prime. However, if we cannot reach a distinct node in V prime in the other branch, we exclude it from the set of weakly deciding vertex. It can happen that we reach a node such as N1 from one branch which does not have a second branch. Then that node cannot lead us to two distinct V prime paths, and we immediately exclude it from the set of weakly residing vertices. In this way, when we reach a node in W, we decide whether we should include it or exclude it from the set of weakly residing vertices. When this process terminates, we obtain the genuine set of weakly residing vertices. What remains is to check the reachability of the previously generated weakly residing vertices from the nodes in V in the control flow graph. All nodes in the set of weakly residing vertices that are reachable from V in the control flow graph are included in the weak control closure of V. Moreover, V itself is included in the weak control closure of V. We have proved that the worst case complexity of the whole process is quadratic with respect to the size of the control flow graph. Please read our paper if you are interested to see the proof. We have implemented our algorithms and the algorithm of Danisic and others in the Silang LLVM framework. We performed experiments on a number of SPEC CPU 2017 benchmarks. In total, we took 7 benchmarks consisting of 2081 kilolines of C code. We generate the VSET randomly, and each experiment was run 10 times, and the results are the average of 10 runs. We measure the execution times in microseconds, which are converted to milliseconds. When comparing the execution time of our method with the method of Danisic and others, we obtain a minimum speed up of 2.9 for the XZ benchmark and a maximum speed up of 23.8 for the GCC benchmark. On an average, we obtain a speed up of 10.6. We ran the same experiments in a virtual machine with a different LLVM, and the randomization procedure generates different VSETs. We obtained an average speed up of 5.4, which is somewhat smaller than the original experiments in the real machine. Nevertheless, both experiments prove that we significantly improve the execution time of computing WCC than the best state of the art methods. We plot the execution time of step 1 and step 2 in our algorithm, which are the expensive steps in our WCC computation. We also have plotted the n, log n, and n square function. The curves are plotted in the logarithmic scale. We see that both steps 1 and steps 2 are closer to the n log n curve for the Perl bench, and they are closer to the linear curve for GCC. We get similar results in other benchmarks as well. We are now close to finish this presentation. We conclude by stating that Sebastian Danisic and others have provided the generalized definition of weak control closure, which can capture control dependencies from a wide range of programs. In this work, we have provided an improved algorithm that is both theoretically and practically efficient than the method of Danisic and others. The theoretical complexity is improved by an order of the size of the control flow graph, and we obtained a practical average speed up in the range from 5 to 10. The practical execution times of our algorithm is closer to either n or n log n curve when the execution time is measured in microseconds. Thus, we conclude that we improved the WCC computation by an order of magnitude. As for future works, we are planning to apply our method to improve the computation of a strong control closure for intra-procedural programs, and we would like to extend the WCC and SCC computation for inter-procedural programs. There exists an interesting link between WCC computation and the generation of a static single assignment program. In our previous work published in the JSS journal, we showed that existing methods to generate SSA programs are not precise. We believe that we can apply the WCC computation method to generate precise SSA programs. That's all from me today. Thank you everybody for listening to my talk. I shall be very happy to answer your questions. Thank you.